Hi everybody, this is Mr. Lee. In this video, we're going to look at a charged particle moving in between two charged plates, but the charged particle is moving perpendicular. Let's begin. Okay, so before we begin, let's get a couple of things out of the way. They're very important for these type of problems. One, it's the actual charged plate themselves. So what I'm going to do is I'm going to draw two charged plates. We'll say charged plate there and a charged plate there. Okay. Now we'll say that the top plate has a uniform distribution. So that means that there are equally distributed positive charges, and below there are equally distributed negative charges like this. Okay. Now these two plates, they will have a E field in between. So we're going to draw that. Remember, the E field always comes out of the positive and it goes into the negative, like so. All right, now the important thing about this is that in between these two charged plates, we see that the E field is perpendicular to the plate itself. So I'm going to draw that right there. Okay, it's perpendicular to the plate itself. And the other thing that I want to point out is the edges. Now, when we take a look at the edges, we get this effect called the fringing, okay, fringe effect, or fringe fields, or the edge effect, where because we technically have positive charges on the end there and a negative charge on the end there, same for here and here, what we get is a E field that bends around like so. Okay, we get E field that bends around like so. It's similar to what happens if we have, let's say, a positive charge here and a negative charge here, where in between we get these lines, but anywhere else we get this bending effect or this fringing-like effect. Okay. All right, and so what we're going to do is for these problems, there's a couple of things that we need to make sure that we are looking at. One, the E field is a constant field. Okay, and in order to ensure that, and we don't want any fringing, no fringing. And so what we want to take a look at is a portion of this charge plate. So let's say we're just only going to look at this portion here. Okay, that middle portion. So we're only looking at this middle portion right there for the sake of this problem. It's either that, or we can call these two plates the length of the two plates is infinitely long. Technically, we can have infinitely long plates, but for the sake of the problem, we want to take a look at either a portion of the two plates or a infinitely long portion. And the reason why we do that is so that we can have two charged plates where there is no fringing. So I'm going to redraw it. Okay, we'll make the top plate positively charged, and we'll make the bottom plate negatively charged, and we'll have a E field that is perpendicular to the plates, and we're going to go from positive to negative. All right, the next thing we want to do is we want to have a charged particle with an initial velocity. So I'm going to draw that charged particle over here. Let's choose perpendicular. All right, so we have a charged particle Q right there, and this Q is moving to the right with a velocity. Okay, so there's a couple of things that can happen when you have a charged particle that's moving in between two plates like this. The charged particle can either move upwards towards the positive plate, like so, okay, or it can move to the bottom plate, like so. Now, the reason behind this is the actual charge of the charged particle. So this charged particle, if it moves towards the top plate, we can say that the charged particle would have a negative charge. But if it moves towards the bottom plate, we can say that it has a positive charge. Okay, because negatives are attracted to positives and positives are attracted to negatives. So either way, it's going to be moving in this parabolic curve. And if you remember from mechanics, this is a path that a object travels when it is being shot out horizontally. So what I mean by that is there should be like classic problems where you have like a table, okay, and we have like a floor, and we have like a marble, or we have a ball, and that ball is shot off the edge of the table and it lands somewhere at a distance X away, or the range away from the table. Now this scenario is very similar to the E field scenario, because if you think about it, we live in a gravitational field, right? And the gravitational field always points downwards like so, much like how I drew the E fields between these two charged plates. So because this object is within a field, it's going to experience the effects of the field. And that is where we're going to begin for this problem. Okay, so we have a charge and it's moving in between two plates. And because this is like a new shape that we haven't seen before, let's choose to focus on the charge that is negatively charged. Okay, so I'm just going to do a quick resketch. Okay, we have a negative, we have a positive, and we have a negative charge, and it's going to be moving upwards like that. All right. The next thing that we need to do is, in order to set up these problems, we have to remind ourselves about horizontal projectile problems. Now, hopefully in mechanics, when you solve these problems, you created a X and Y table, because the object or the charge is experiencing both X motion and Y motion. Now, I always encourage my students to create a table with all of the kinematics variables, and I also encourage you to do this for these types of problems too. So we have our initial position, our final position, our initial velocity, our final velocity, our acceleration, and our time. Now, if you're wondering, Mr. Lee, how do you always have it in that order? Well, if you think about it, these are just the derivatives, right? So the derivative position is velocity, the derivative velocity is the acceleration, and it's all with respect to time. Okay, so let's create that over there. All right, now this is a great reminder of the rules we set in place for horizontal projectile motion problems. Now, depending on your problem, these rules might change, but unless they throw curveballs at you, here are a couple of rules that will always be in place. And I'm going to do these in red so that it stands out. One, we always say that our initial position is going to be 0 meters, right? That's usually always the case. Because that's where we start off, and where we land, our range will be our final position. Our initial velocity and our final velocity is just our initial velocity. Okay, that doesn't change. Our horizontal velocity will not change because a lot of the times we do not have acceleration along the horizontal axis. Okay, all right. The other thing that we need to look at here is for the y-axis. Now, for the y-axis, our initial starting position, well, I've always seen it usually around halfway in between the two plates, but that can always change, so that's not a usual go-to. Same with the final landing position. If it lands on the bottom plate, we can say that the final position is 0. If it lands on the top plate, it's just the height between the two plates or the distance between the two plates, so it really does matter. So we can say it's either going to be 0 or it could be the change in height between the two plates. Okay, so it really does matter. It depends on your situation. Our initial y velocity is always 0 meters per second because initially it's not moving in the vertical axis. Okay, it's only moving horizontally. It's just that when it's under the effect of the E field, that's when it starts to move vertically. All right, now this acceleration. If you remember, we usually said that the acceleration in the y-axis was equal to g. However, depending on your problem, that won't always be the case, right? So this is something that you should be finding out. And of course, time is the time of the travel, and it's the same for both. Okay, so I'm going to do a quick little highlight of the things that stay true here. Okay, so these are usually the things that will always be true for our scenarios. All right. Now, how do we solve these types of problems? Well, if you remember from the kinematics unit, we usually stick with the y-axis first. And the reason behind that is one of the things that you need to always find out is how long it takes for this projectile to travel. Okay, so once you unlock that time component, you can figure out the rest of the problem. Now, I say this with a caveat, that's like about 95% of the time, you have to figure out the time first. And it really does depend on the situation, but knowing the time really does help. Okay, so knowing that we need to probably look at the y-axis here, okay, how do we set up the y-axis situation? Well, one, we need to figure out the time. In order to do that, one of the things that you have to unlock is this acceleration component. Okay, we need to know the acceleration of this charged particle. This is slightly different from mechanics because we usually said that the acceleration of the y-axis was g, or negative 9.8 meters per second squared. So let's think about this. Let's go back to my original drawing up here to figure out how we can solve for the acceleration. Now, when this charged particle, okay, is not moving horizontally, but it's just within the E field, in order to figure out the acceleration of it, remember, with acceleration, we're usually dealing with forces, and in this situation, it's not any different, okay? We can draw a free body diagram. And let's just say, for continuity's sake, we'll say that this is a negatively charged particle, okay? We'll say this is a negatively charged particle. So if this is a negatively charged particle, it will experience an electric force going up, Fe. And that's fantastic because if we know that, we can set up our net force formula. I'll show you that below, where the net force is equal to mass times the acceleration, okay, and that's the mass of the charge, is equal to EQ, where E is the E field strength and Q is the magnitude of the charge. So the acceleration is going to be EQ divided by M, if we are rearranging the variables in that sense. Okay, now this is true if and only if there are no other outside forces. And what I mean by that is you might come across a situation where this charge is also under the influence of the gravitational field, and in that case we have to have F of G there, and that just means we just have to have an additional mg in our net force formula. All right, now with that out of the way, the only thing that's left for me to really show you is the kinematic equations. Now this is also in your formula sheet, but it's good to have down in your notes. So we have the classic change of position is equal to initial velocity times time plus 1/2 at squared. We have the final velocity, which is equal to initial velocity plus the acceleration times the time, and of course the final velocity squared, initial velocity squared, plus 2 times the acceleration times the displacement. Okay, and with that, with this acceleration unlocked, you can use any of these three formulas. Now, I just want to point out that these three are for only accelerated objects. Okay, or any particle or object experiencing acceleration. And the reason why I say that is, if you take a look here, if your acceleration is 0, if your acceleration is 0, if your acceleration is 0, the formula does in fact fall apart. And this is another opportunity for me to remind you, if you are experiencing 0 velocity, you can use a formula that we first introduced to you way back when. It's probably one of the first formulas you saw. It is for objects experiencing 0 velocity. So velocity is just displacement over time. Okay. Yeah, and we usually use that for the x-axis there. Okie dokie. All right. That is how you set up and how you can solve for a charged particle moving in between two plates when the charged particle is moving perpendicular to the plates. I'll see you next time. Bye-bye.